Good day, everyone. We're reviewing Wetzel's Limnology textbook, and this is edition number 4, chapter 6, Lights in Inland Waters, with Kevin C. Rose and the Department of Biological Sciences at Rensselaer Polytechnic Institute in Troy, New York, United States. Solar radiation is a fundamental regulator of aquatic ecosystem dynamics. The absorption of solar energy and its dissipation as heat have profound effects on the thermal structure, stratification of water masses, and circulation patterns of lakes and other water bodies. Light influences numerous aspects of nutrient cycling and the distribution and behavior of dissolved gases and biota. Nearly all energy that controls the metabolism of lakes and streams is derived from solar energy via photosynthesis. Light as an entity. Ecologically, the term light often does not have a consistent use due to the different ways in which it is measured and the term applied. First and foremost, light is energy, something that is capable of doing work and of being transformed from one form into another, but can neither be created nor destroyed. Radiant energy can be transformed into heat that modifies the vertical structure of aquatic ecosystems, as well as the metabolic rates of organisms, or into potential energy via biochemical reactions such as photosynthesis. Energy transformations are far less than 100% efficient in a system such as a lake, and most radiant energy is dissipated as heat. Units and definitions. Here the term lights refer to the portion of the electromagnetic spectrum that reaches Earth's surface and provides energy for biological, biogeochemical, and other ecological processes. All electromagnetic radiation has both particle, for example photon, and wave properties. Wavelength, lambda, is an important quantitative parameter of any periodic wave motion, including light and water movement, and is defined as the linear distance between adjacent wave crests. A photon is a pulse of electromagnetic energy and has an associated wavelength and frequency v, or mu, which are inversely related by the equation of lambda is equal to c over v, where c is the speed of light, which is 2.998 by 10 to the 8 meter per second in a vacuum, and the electromagnetic spectrum is expressed as unit of frequency cycles per time and wavelength, typically 10 nanometers, 10 to the minus 9 meter. Wavelength can also be expressed as a wave number, so V1 or K, which is the number of wavelengths per centimeter. So here in figure 6-1, we have the solar irradiance at the surface of the Earth at sea level, showing major absorption from atmospheric oxygen, ozone, and water vapor. So we have the ultraviolet range here, we have the visible range here between 500 and I think it's probably like in the 600 maybe. Then we have the infrared range, which is the heat causing range. So the wavelength is in nanometers, and then the irradiance is watts per meter squared per nanometers. And so we see that ultraviolet, visible, and infrared represent 5%, 45%, and 50% respectively of the solar radiation energy reaching Earth's surface, creating using the SMARTS model version 2.9.5 to generate the solar spectrum similar to STM standard G173-03. So what you see here is that a lot of the energy that reaches the Earth in terms of usable energy is in the visible range. So this is the whole purpose of the text here. So for most practical purposes, and with few exceptions such as hot springs, solar radiation constitutes all of the energy input to aquatic ecosystems. Colors in a portion of the electromagnetic spectrum that can be perceived by the human eye are all associated with wavelength ranging from violet, 400 to 450 nanometers, to red, 650 to 700 nanometers. However, it should be noted that the limits of the visible spectrum are not sharply defined and vary among individuals, and many aquatic organisms can perceive wavelengths completely outside of the range of the human eye. Visible wavelengths are similar to the portion of the solar spectrum used by photosynthesizing organisms, otherwise known as photosynthetically active radiation of PAR between 400 and 700 nanometers. These relatively narrow wavelength range account for about 45% of the energy reaching Earth's surface. At wavelengths longer than visible wavelengths, greater than 700 nanometers, is infrared radiation, which accounts for about half of all incoming solar energy. At wavelengths shorter than visible wavelength is ultraviolet radiation, including UVA, typically defined at between 320 and 400 nanometers, and UVB, typically defined between 280 and 320 nanometers, and UVC, typically defined as 200 to 280 nanometers. UVC and some UVB are not found naturally on the modern Earth's surface. The shortest wavelength penetrating through the atmosphere and reaching Earth's surface is typically around 290 nanometers. UV accounts for about 5% of the energy reaching Earth's surface. The amount of light per unit area, otherwise known as radiant flux density or irradiance, is quantified by counting quanta or measuring energy. Visible light, or PAR, can be expressed either as moles of photons per unit area per unit time, macromoles per meter square per second, otherwise known as photosynthetic photon flux density, or PAR irradiance, which is in watts per meter square, otherwise known as photosynthetic radiant flux density. A related term is the photosynthetic photon flux fluence rate, which is the total number of photons incident on a point from all directions. PAR is typically measured in quantum units, for example, macromoles per meter square per second, while higher energy shorter wavelength UV radiation is typically measured in energetic units, for example, watts per meter squared. But conversions vary among subdisciplines, conventions vary among subdisciplines, and it is possible to convert between the two. At noon on a summer day without clouds at temperate latitude, PAR is approximately 2,000 macromole per meter squared per second. This value can be converted to energetic units using Planck's law, which describes how the energy content measured in joules of photon of a known wavelength is inversely related to wavelength via E is equal to h over mu, or hc over lambda, where h is a Planck's constant of 6.63 by 10 to the minus 34 joules second, expressed energetically. A PAR of about 2,000 macromoles per meter squared per second is about 430 watts per meter squared. Converting PAR from energetic to quantum units requires information on the spectral composition of the light field. In the absence of those data, an approximate conversion factor of 2.77 by 10 to the 18 quanta per joule, equivalent to 4.7 micromoles per quantum per joule, can be used. Dynamics of incident solar radiation. Atmospheric characteristics regulate the amount of solar radiation impinging on the surface of aquatic ecosystem, and dynamics in the atmosphere introduce variability in surface irradiance over timescales from seconds to millennia. As solar radiation penetrates and diffuses in the atmosphere, the energy of wavelength is differentially attenuated by absorption and scattering processes. According to Rayleigh's law, light scattering by gas molecules in the atmosphere is proportional to 1 over lambda to the fourth, meaning that shorter wavelengths are scattered substantially more than longer wavelengths. This effect gives the sky a blue color to the human eye on cloudless days, and the reflection of the scattered skylight contributes to the blue color of many water bodies. Atmospheric light scattering also regulates the amount of indirect solar radiation reaching Earth's surface. In contrast to indirect solar radiation, direct solar radiation is largely regulated by the sun angle and the atmospheric distance through which the light must pass. The amount of light received at a water body surface known as incident solar radiation varies with sun angle, elevation, cloud cover, atmospheric aerosols, ozone or O3, and other gas concentrations. Ozone strongly absorbs short wavelengths UVB rays, and this is largely responsible for wavelengths below about 290 nanometers, not reaching Earth's surface. However, ozone does not substantially affect UV wavelengths above 330 nanometers. Water vapor and carbon dioxide strongly absorb infrared radiation and hence are important gases contributing to the greenhouse effect. Anthropogenic air pollution also contributes to the attenuation or the reduction of light with depth or distance of incoming solar radiation and is variable through time and space. Often, high concentration of anthropogenic air pollution in the form of aerosols give the sky a brownish hue which can be visible over some urban areas. Sun angle is the most important regulator of variability in irradiance over the timescale of days to seasons. The sun angle is measured relative to an angle directly overhead and is known as the solar zenith angle. This angle regulates the distance through the atmosphere that light travels before reaching an object, called the air mass effect. Solar zenith angles vary substantially with latitude, day or year, and time of the day. In equatorial regions, sunlight impinges closer to vertically throughout the year, leading to muted seasonal variation in energy inputs. In temperate and polar areas, however, the sun angle changes substantially seasonally and thereby regulates many phenological processes. In polar extremes, direct solar energy decreases to zero for over 1/3 of the year, and polar waters then receive thermal radiation only from indirect sources. Time of day is another factor that strongly influences the solar flux reaching the surface of water bodies, as the sun angle impacts the distance that the path of light must travel through the absorbing atmosphere. So let's look at figure 6-2 here. So we have two figures. We have A and B, and that shows variations in incident photosynthetically active radiation, or PAR, associated with variation in solar zenith angle. So A is noontime PAR across seasons at different latitudes. So red is 20 degree north, which is right below the tropic. Blue is 40 degrees north, which would be, at the latitude of Northern California. And then purple, which is 60 degree north, that would be just south of Anchorage, Alaska. And then B, over the course of a day, during different times of the year, at 40 degree latitude. So on the x-axis, we have month here, and then we have the time of the day here, and then incidence, and then here we have water, so we have the amount of energy that is received, which is watts per meter squared. And then here we have the same, okay? So what we see is that for the location that is close to the tropic, we don't have a lot of change in the incident, in the amount of energy reaching the Earth on any given month within a year. And then as the latitude increases, we see a large difference. So for example, like at the latitude of Anchorage, Alaska, we are seeing like that most of the energy at the highest level is is reaching the Earth in the summer month, right around the summer solstice. So this is a curve for the blue curve, which is the 40 degree north latitude. And we see the same kind of variability, but this is over a day. So at the winter solstice, you can see that we don't have as much solar irradiance, and that most of the solar irradiance happens for all the days around noon, which is solar noon. And then equinox, which is when we get the same amount of light and darkness for a day. So we have the fall equinox, and then we have the spring equinox, and then we have pretty much a curve that is the midpoint between the summer solstice and the winter solstice. So summer solstice, of course, showing the highest amount of solar irradiance, especially at noon. Okay, and we were, let's see here. All right, long-term radiation. So let's see here. In addition to the above described factors, scattering and absorption also increase in moist air, which is more common on the downwind side of large water bodies. The elevation of a lake also influences the quantity of atmosphere through which solar radiation must travel, and therefore the amount and spectral composition of incident light reaching the water body. The amount of solar irradiance on the Earth's surface varies over time. Decadal scale increases and decreases in anthropogenic air pollution have caused corresponding decreases and increases in incident solar radiation. A widespread decline in incident solar radiation was observed for decades up to around 1990 across Europe, North America, and East and Southern Asia. This phenomenon has been referred to as the global dimming. Since then, observation generally indicates a partial recovery and increases in solar radiation in some regions across Europe and North America, a phenomenon referred to as brightening. These trends are believed to be driven predominantly by long-term increases and then decreases in anthropogenic aerosols. So anthropogenic aerosols are anthropogenic or human-made pollutants that are in the air, that are within the column of air. And so they are like, for example, the results of burning coal, and that is inputting these particles into the air and decreasing the amount of solar irradiation through the surface of the Earth. Long-term changes in ultraviolet radiation have also occurred due to changes in the ozone layer. Chemical pollutants, primarily chlorine and bromine in chlorofluorocarbons or CFCs, led to a thinning of the ozone layer and consequent long-term increases in ultraviolet radiation, particularly in Antarctica and adjacent regions in the later half of the 20th century. Total ozone column declines of about 3% per decade were observed until the mid-1990s. International agreements such as the 1987 Montreal Protocol have since been successful in reducing emissions of ozone-depleting substances. Consequent ozone stabilization and recovery has begun with a return to pre-impacted ozone layer thickness, predicted by the mid-21st century. However, recovery may be delayed due to climate change.